right now we're going to be doing some proofs by contrapositive. If you haven't checked out my intro to proofs video, definitely do that and take a look at some of the other kinds of proof videos as well. Let's recall from our intro to proofs that a lot of theorems are written as if-then statements, and even if they're not, you can rewrite them to be if-then statements. So that's something like P implies Q. So by the laws of propositional logic, P implies Q is equivalent to not P or Q by conditional identity, and then that's the same as Q or not P just by commutative. And then we can say that not Q or not P is also equivalent by double negation, then that's the same as not Q implies not P, again by conditional identity. So that means that if we're proving if this, then that, it's logically equivalent to say if not that, then not this. So basically proving not Q implies not P is enough to prove that P implies Q. That's the basis of what a proof by contrapositive really is. So why would we want to do that? Sometimes it's hard to show if this, then that, and it's easier to show the reverse. And sometimes the conclusion will have more like easy moving parts in it than the hypothesis, and we'll look at some examples where that's really the case. Let's take a look at our general proof sketch for a proof by contrapositive. So once again, we always state our theorem, and we always make sure to state it in a P implies Q, if this, then that kind of statement. So then we should say that we're proving by contrapositive, i.e. we will show that not Q implies not P. That's super important for this kind of proof because you want to keep it clear to yourself and to your reader how you're going to be proving things. Just like a direct proof, we'll state all our definitions and then plug our definitions into our statement, do some manipulation, some arithmetic, all that fun jazz stuff, and then come out with the conclusion of the contrapositive. So if we're proving if the original theorem is P then Q, what we should end up coming out with is not P is true, because that's the conclusion of the contrapositive. Whew. So let's do an example with just words first. So let's say my statement is everyone that has a good grade took the test. Let's first rewrite that as an if-then statement, and then see if we can rewrite it as something that has quantifiers in it. So I can say, if you're someone that has a good grade, then you took the test. So our next step is saying that we're proving by contrapositive, and we should specifically state the new statement that we're trying to prove that's logically equivalent to our original one. So if you didn't take the test, then you don't have a good grade. Let's state the definitions first, okay? So taking the test means submitting responses to test questions, and then obviously not taking the test means that you didn't do that. A grade is determined by the accuracy of your responses, and when you don't have any responses, your grade is equal to 0. 0 is a bad grade, which is in particular not a good grade. So let's plug all our definitions into our statement. So you didn't take the test is equivalent to you didn't take the test is equivalent to you didn't submit responses for test questions, which means you didn't have responses, and which means you got a 0, which is a bad grade, which is not a good grade. So if you can see, we just use a bunch of logic things to get to our conclusion by only assuming that our hypothesis was true. So you might be asking, why didn't we just do a direct proof then? And I would say that usually we use contrapositive when the conclusion is a little bit easier to wrap our heads around. So for this example, it's kind of hard to say, look at everyone in this class that has a good grade, because we usually think of grades as results of tests and not tests as the results of grades. So let's do an example with even and odd numbers. And my statement is, if m times n is even, then m or n is even. Let's say that we're proving this by contrapositive, and if you can tell with this problem, it would be really hard to do this by direct proof because our m and n are separately defined in our conclusion, and state the new statement that we're trying to prove. So if m and n are odd, then m times n is odd. And remember, we can use De Morgan's law on this to see why it has to be m and n are odd instead of just m or n being odd in the new hypothesis. Once again, let's state our definitions. the value of m, the value of n in integers, and let's plug our definition into our statement. So we have this now, and then we do some manipulations, right? We do some arithmetic, and we see that m times n, it's equal to 2 times k times j plus j plus 1 at the end. So we can make some conclusions about that, right? The product of 2kj is an integer because the integers are closed under multiplication, and then the sum of those three terms is an integer because the integers are closed under addition. Then m times n is equivalent to some integer times 2 plus 1, which is the definition of an odd integer. So we've come out with the conclusion of our contrapositive, and we've essentially proved both our contrapositive statement and the equivalent original statement. Let's look at our final example, which will be numbers, but for rational and irrational numbers. Our statement is, if m times n is irrational, then m or n is irrational. So once again, the separate things like m and n are separate terms in the conclusion. So it's a little bit easier to use contrapositive for that because it switches the order. And another good hint at when you're supposed to use contrapositive is when you have a lot of irrational numbers. We don't really have a good pretty definition of an irrational number, so it's much easier to do contrapositive for these questions. The opposite of an irrational number is a rational number, and we can make lots of definitions and statements about those. So the contrapositive of that original statement is, if m and n are rational, then m times n is rational, which is a much easier statement to prove. So we state our definitions once again. And really, these definitions would be so much harder to come by if we'd left m or n as irrational numbers in our original question. So then we plug our definitions into our statement. We say m times n is equal to j over k times p over q. We do some manipulations, that's just multiplying in this case. And then we come out with the conclusion of the contrapositive, right? JP and KQ are both integers because the integers are closed under multiplication, and then K times Q is not equal to 0 because neither K nor Q is equal to 0. Then MN's product is an integer divided by an integer, which is exactly a rational number. Thanks for watching, and stay tuned for the other kinds of proofs.